Good afternoon, everyone. Welcome back. We are now going to start one of the 4 short courses in the 4th Conference on Statistics and Data Science, and I hope you enjoy. This short course it will be about symbolic data analysis. It will be on parametric multivariate analysis of interval data. For those that are not sure what that means, soon you will be aware of that. This course is going to be given by 2 colleagues and friends from Portugal, Paula Brito and Pedro Duarte Silva. Paula, she is an associate professor at the Faculty of Economics of the University of Porto and member of the Artificial Intelligence and Decision Support Research Group of INESC TEC Portugal. She holds a doctorate degree in applied mathematics from the University of Paris Dauphine and an habilitation in applied mathematics from the University of Porto. Her current research focuses on the analysis of multidimensional complex data known as symbolic data, for which she develops statistical approaches and multivariate analysis and methodologies. She has been involved in 2 European research projects and coordinate the Portuguese participation in the H2020, the Horizon Framework FinTech project. Paula was president of the International Association for Statistical Computing between 2013 and 2015. She has authored a large number of research papers in highly ranked journals in her field of research, and has been invited speaker at several international conferences. She's a regular member, is invited
Hello, everyone, and hello, Maria and Pedro. I think we're having some technical problems. I believe we lost Paulo for a bit. Can you guys hear me? I believe that you have your mic.
Agora sim.
research folk.
Okay, Paulo is back.
Agora sim.
I don't know where it was break.
Yeah, we lost you for like 30 seconds, maybe.
Yeah, I lost you when you were finishing my presentation.
All right, okay. So Paula, to finish the presentation of Paula, she is very much involved in research. She has published a lot of research papers in high impact journals, and she is also invited quite often to be part of the international program committee of scientific conferences, and she shared the 2 main conferences, one in 2008, the COMPSTAT, and one in 2022, the IFCS. As for Pedro is an associate professor in the Catholic Porto Business School and member of its research center. He holds a doctorate degree in business administration from the Terry College of Business of the University of Georgia. His research focuses on the intersection between data analysis and machine learning, multivariate statistics, and operations research, with a particular focus on development of novel methodologies for the analysis of big and complex data. He is the author of numerous communications at reputable scientific conferences, and his research has been published in highly ranked scientific journals, such as the European Journal of Operations Research, Computational Statistics and Data Analysis, Decision Science, Computational Statistics, and Journal of Multivariate Analysis. This is just a short introduction of Paula and Pedro. They are very active in the scientific community, nationally in Portugal and internationally. So it is for us a great pleasure to have them here, for them to share a little bit of their work, and in this case they will teach us a little bit on symbolic data analysis. For those of you that are not aware of what that means, we are looking forward to hear about it. Paula and Pedro, please, the floor is yours now. Thank you.
Thank you very much, Paulo. And first and foremost, we'd like to thank the organizers of CSDS 2022, and particularly Professor Paulo Canas Rodrigues, for the opportunity to present our work and our development, and hopefully motivate you to this new area of data analysis, which is called symbolic data analysis. Can you please just confirm that you are now seeing our screen?
We do.
You do, and do you hear us well, right?
Yes, perfectly.
Yes. So as Paulo already mentioned, I'm Paula Brito. I'm currently professor at the Faculty of Economics at the University of Porto and member of the Laboratory of Artificial Intelligence and Decision Support of INESC TEC. At the University of Porto, I teach usually statistics at undergraduate level and multivariate data analysis at postgraduate level.
I'm Pedro. I'm currently at Católica Porto Business School, and I'm a member of Centro de Estudos em Gestão e Economia of the Universidade Católica Portuguesa. And I also teach statistics and data science and operations research at undergraduate and graduate levels.
Okay, so we'll start our short course. Please, everybody, feel free to interrupt or ask questions if you have any doubts. And so let's start. So the course will be divided in two parts. In the first part, we will introduce symbolic data analysis, so to let you know what it is about, and see that it proposes a new framework where we can take into account data with variability. So we'll try to motivate you for the situations where you have variability in the data, which should be represented in an appropriate way and dealt with. This has led to the need to define new symbolic variables, new types of variables, and we'll particularly focus on two types, interval valid and distribution valid variables. Then the remaining of the course will concentrate on interval valid variables, for which we'll propose parametric models. All along the course, we'll be using an R package developed for the analysis of interval data, which is called MyData, Modeling and Analyzing Interval Data, which is an R package. And I believe Paulo has already shared a link from which you can download the R script that we'll be using. And those that want to use the package along the course with us should install this package. So we'll then introduce the parametric statistical models, probabilistical models appropriate for interval data, proceed to maximum likelihood estimation for all cases, and then address robust estimation, which allows for outlier detection. This will conclude the first part. In the second part, after a short break, we'll proceed to multivariate analysis methods, covering clustering, discriminant analysis, and analysis of variance. So let's talk about the data. In what we now call classical data analysis, as everybody knows, data is represented in an n rows times p columns matrix or data array, like the one here, where each of n individuals, also called cases, units, usually in rows, take one single value, numerical or categorical, for each of p variables, usually in columns. In this small data array, we are describing flights by the corresponding number of passengers, delay on arrival in minutes, the airline, and the distance of the flight. But sometimes data is not so simple. Data may comprehend variability. When does this arise? Variability occurs when, and to talk first about the flights example, when we have data about the flights, but you are not interested in analyzing the flights per se, but to analyze the airline companies as a whole, and not each individual flight. or when you have data about patients, but you want to analyze the hospitals and not the individual patients. Or you have data about players, now in the time of the Football World Cup, but you do not want to analyze or compare the players themselves, but the teams, which are groups of players. In general, if you have data about people, about citizens, like in official statistics, often you are interested in analyzing parishes, cities, sociological groups of interest, and not the individual citizens. In all these cases, you need to aggregate the individual data, the micro data that has been collected, so as to get a description of the entities of interest, the hospitals, the airline companies, the teams, or the cities, so that you get macro data. In those cases, to take into account the variability that appears when you aggregate the data, the variable values will no longer be single numbers or categories, but rather finite sets, intervals of real numbers, or more generally, distributions on an underlying set of subintervals of categories. We say that we go from the microdata that was collected to macro data, as it is the case here. If we aggregate data corresponding to individual flights in terms of the corresponding number of passengers, delay on arrival, and type of aircraft, so as to get descriptions for the different airline companies, then we can aggregate the number of passengers for all flights from each airline, for instance, by an interval between the minimum and the maximum values for the number of passengers. We can have the distribution of the delay on arrival. And in this case, we'd say that for airline A, in 25% of the cases, the delay was less than 10 minutes. In 65% of the cases, the delay ranged between 10 minutes and half an hour. And in the remaining 10% of the cases, the delay was larger than half an hour. The type of aircraft can also be aggregated in terms of a distribution. And here for airline A, we understand that in 60% of the flights, this was a Boeing, and in the remaining 40%, the aircraft was an Airbus. And correspondingly, for the different airlines, B, C, and whatever we get, we can have the interval of number of passengers for the corresponding flights in the period of interest, distributions of the delay, and of the type of aircraft. Is this something new? Is this now recent that people are interested in aggregated data and need to take into account variability? Not at all. Of course, this existed before, but the classical way of treating this problem is to represent the aggregated data via central statistics, like a mean or a median if you want to be more robust, or a mode for the case of categorical variables. But by doing so, we lose a lot of information. We lose all the variability that was observed in the original microdata that has been aggregated. Symbolic data analysis proposes a framework where data can be aggregated at the granularity level of interest and still variability be kept, so that we keep much more information than just by taking a central statistic. Of course, we need to introduce new types of variables. As you see now, in each cell of the data array, we do not have just a single number or a single category, but we can have intervals, sets, or distributions on subintervals or sets of categories, like in this example here. Such data that is called symbolic data may indeed arise from the aggregation of microdata, and this is perhaps the most common source of symbolic data. This aggregation may be contemporary or temporal, as we'll see in the next small examples. But we can also have symbolic data directly, as it appears in the description of abstract concepts, and we'll soon present an example of such case. So the aggregation of microdata can be made a long time, like in the example of flights. If we have flights observed a long time, then after the period of interest, we can aggregate data for the different airlines by taking, for instance, the interval of the number of passengers, delay upon arrival, type of air distribution of the types of aircraft, and so on and so forth. In this case, the airlines that were observed in the microdata are also our units in the microdata. But we aggregated the different observations for each airline that occurred a long time. In this next example, the original data was cross-sectional data observed at a given point in time. And here you have official data from the United States. And this is data by community. Each community belongs, of course, to a given state in the United States of America. And you had for the given community the per capita income, the percentage of population that lives in poverty, the percentage of non-occupied houses, the number of people per occupied house, and the percentage of kids who live with their two parents. This is by community. But if we are interested in analyzing and comparing the states and not the individual communities, then we should aggregate this data for each state, aggregate all the values for the communities in each given state. This is contemporary aggregation. The data is cross-section and keeps being cross-section. But now the units, the statistical units are no longer the communities, but rather the states. And by aggregating data for all communities in the state of Alabama, for instance, we get an interval for each of the variables since they were all numerical. And we can say that at this point in time, when data were collected in the state of Alabama, in the communities of the state of Alabama, the per capita income ranged from 5,820 to 39,610. The percentage of people living in poverty ranged from 2% to 44%. The number of people per occupied house ranged between 2 and 3, and the percentage of kids living with the two parents between 30 and 90%. This is the range of values. Okay. But as I mentioned just before, we can also have symbolic data that come directly as in concept descriptions. Take this nice example of the description of a dog that you may find, for instance, online. And dog, for different variables, here we took just 4, can be described, the species of dog, as having a coat that may be single or double, a vision that ranges between 500 and 900 meters, a hearing frequency that ranges between 40 and 60,000 hertz, or smell receptors that range between 125 and 220 million. So this means we are not describing one dog, not my dog or the dog of my neighbor. We are describing what is the species dog. And of course, there's a lot of variability. There are many different dogs. So here we see that for the code, the value of the variable is a finite set. For the other variables, this is an interval. These are intervals. And this is native symbolic data. It did not result from aggregating a data set of microdata. It's the description as it is proposed scientifically in zoological data, in zoological texts. So as we have seen, the need to represent the variability intrinsic to the data that may appear when we have aggregated data or data describing concepts rather than single individuals led to the need to introduce new types of variables. Let's see something about this. In classical data analysis, we usually classify the variables as numerical, also called quantitative, or categorical or qualitative. These are now what we call numerical single-valued variables or categorical single-valued variables. These are the classical ones, where for each unit, each individual, a single numerical or categorical value is recorded. But now, to take into account variability that may be intrinsic to the data, we introduce new types of variables. Continuing to classify them as numerical or categorical, we'll consider numerical multivariate variables where the value of the variable is a finite set of real numbers, interval valued variables where the values are intervals of real numbers defined usually by a mean and a max, or histogram valued variables where a distribution over a finite set of subintervals is recorded. In the categorical case, together with the classical ones, we introduce multivariate variables where the recorded value is a finite set of categories, or categorical model values where you record a discrete distribution over a finite set of categories. Let S be the set of the finite set of the n units to be analyzed, and let's call y1 to p the descriptive variables. Let O underscore j be the underlying domain of each variable yj, and bj the observation space, that is the set where variable y takes its values. Now let's consider the different cases. In the classical situation, let it be numerical or categorical, that is the single valid variables, b and o are one of the same things, because the observation space is just the underlying domain. The values of the variable are single values of o. In the case of multi-valued variables, numerical or categorical, b is the power set of O, that is the set of non-empty subsets of O. In the case of interval-valued variables, B is the set of intervals defined in O, which is in itself contained in R. For distribution-valued variables, which we call categorical model in the categorical case and histogram valued in the numerical case, B is a set of distributions over O. Let's focus a little bit more on the interval valued variables, which will be the topic of our course today. And again, S is the set of units to be analyzed, and Y are the descriptive variables. In this case, I associates to each unit in S an interval of real numbers. So Yj of each Si in S is an interval described as usual by its lower and upper bound. Of course, Lig, the lower bound, is less or equal than the upper bound. So B, the observation space, is now the set of intervals of an underlying set O, which is a part of the real numbers. Our data array now, that we may call I for interval, is again an n rows times p columns matrix, which gathers the values of p interval variables on S. That is, each Si element of S here is represented by a so-called vector of intervals. So the observation for each Si is a vector or a list, to be a bit more precise in language perhaps, where each element is an interval, the value of each interval valued variable Yg for the unit Si. So that our data table looks like this. We have n units in rows, p variables in columns, just like in the standard case, in the classical case, but now in each cell of the data array, we have an interval defined by the lower and the upper bound. Examples that we have already seen before, but let's take some more. Suppose that three people, Albert, Barbara, and Caroline, are characterized by the amount of time that they need to go to work. Of course, this varies from day to day. And we may say that Albert needs 15 to 20 minutes, Barbara needs 25 to 30 minutes, and Caroline needs just 10 to 20 minutes. The value of the variable time is an interval. It varies along time. Or another example, if we look at the number of passengers in flights for different airlines, as in the examples that we have already seen before. in the period of interest, airline A had flights where the number of passengers ranged from 150 to 200, whereas for airline B, the number of passengers ranged from 180 to 300, and for airline C, from 200 to 400. Interval data often occurs directly, and this is what we call native interval data. And by directly, I mean not from the aggregation of underlying microdata, but because it is recorded directly as an interval. And a very typical example of this is meteorological data. Look at this example. In this example, we record temperatures and pluviosity in different meteorological stations in the United States. And here we gather the temperatures in January and July and the annual pluviosity. And these are given by ranges, as recorded in this data table. For instance, Huntsville in Alabama had a January temperature ranging between 32.3 and 58.8 Fahrenheit degrees, whereas the pluviosity in 1 year in Huntsville ranged from 3.23 to 6.10. So meteorological data provide directly interval value data, and because it's direct, it's usually called native interval data. This also appears frequently in description of botanical species, specific disease, and so on. For instance, when a person has flu, or when the doctor describes a flu, it usually says the temperature of the body when the person has a flu ranges from 37 to 39 degrees Celsius, for instance. It's always an interval because it varies. It's not a fixed value. Now, if we are aggregating microdata and we have a lot of unities at the micro level, we may wish to keep more information than just the minimum and the maximum in the form of an interval. And this is possible if we consider another type of variable, distribution value data. Take again the example of airlines. And in what we have already showed before, we may gather the values of the delay upon arrival in minutes as a distribution. And here we'll say that for airline A, 25% of the cases, the delay was less than 10 minutes, 65% of the cases between 10 minutes and half an hour, and in the remaining 10% of the flights, it was between half an hour and 1 hour. And we've already seen the aircraft in 60% of the cases Boeing and the remaining ones Airbus. So if we have enough data at the micro level that it makes sense to gather a distribution and not just rely on minimums and maximums, then this allows us to keep still more information than just interval data. Histogram valued variables are distributional values for numerical variables. Here now B is the set of probability of frequency distribution over a set of subintervals, as here 0 to 10 minutes, 10 to 30, and 30 minutes to 1 hour. So the value of a histogram valued variable is now a list of couples, each couple formed by an interval and a weight. This weight is the probability of frequency associated with the corresponding interval. And we shall assume that the sum of the different weights is equal to 1. So for each unit Si in S, the value of histogram valued variable Y may be represented by what we usually call an histogram, and subinterval and a weight, subinterval weight, subinterval weight, and so on. We generally assume, and as we have always been taught in descriptive statistics introductory courses, that within each subinterval, the values of the variable for each unit are uniformly distributed. Of course, when data is recorded, for each variable, the number and the lengths of subintervals may be different, so that some pre-processing may be needed. And just let's note that interval valued variables are just a particular case of histogram valued ones. When the value of a variable y for an unit is an interval, this is like having a histogram with just one subinterval with weight equal to 1. In the categorical case, when we have distributional data, we say we have categorical model variables. They rely on a finite domain of categories, M1 to Mk, and the categorical model variable is a multi-state variable where for each unit we record both a category set and then for each category in this set a weight, frequency or probability, which indicates how frequent or likely that particular category is for this unit that we are describing. If the data results from the aggregation of microdata, then the weights are generally frequencies, and they represent the proportion of individuals of the underlying microdata set, which are characterized by this category. So again, and a bit like in the histogram case that we saw before, the value of a variable is a list, which elements are pairs composed by categories and weights. So where for histograms we had subintervals, we now have categories. And the sum of the weights is assumed to be equal to 1. This type of data is usually analyzed in the framework of so-called compositional data analysis, so that we'll not be focusing on it longer. Examples of this would be, for instance, describing departments of university. Say that you have one department where you have 3 assistants, 5 assistant professors, 1 associate and 1 full professor, and another department composed by 2 assistants, 4 assistant professors, 3 associate professors, and 3 full professors. Of course, if on a very basic way, you just take the modes, you will say that the 2 departments are similar, both mainly composed by assistant professors. Still, we notice that their composition is rather different. And taking the distribution of the 4 categories of professors allows us to take much more information and understand that they are quite different. So now we proceed to interval data. The remaining of the course is only about interval valued data. I hope I have now motivated you for symbolic data analysis and that by now you have an idea of what it is about. Symbolic data analysis provides means for the representation and then the analysis of data, which comprehends inherent variability, either because it arises from the aggregation of microdata, of large sets of microdata, or because it is available directly as such, because it results of descriptions of concepts, or it's directly recorded just by ranges of values. So now we focus on interval data. So data, as we have shown before, that looks like this data array here in this slide. N units 1 per row, P variables 1 per column, and in each cell of the data array, an interval, a range of values for the corresponding variable.
Okay, so as Paula said before, we are not now going to focus on the analysis of interval data. And in particular, we are going to use throughout the next part of the course on an R package called Make Data, Model and Analyzing Interval Data, in which interval data are represented and also includes several tools for analyzing those type of data. In the package Make Data, we have special classes for interval data that try to replicate for those of you that are used to using R, you may know the data frame class, which is the typical data array structure for analyzing a data set of classical data. We will have in Make Data an e-data type of object that tries to replicate the same properties of a data frame, but in which the units, instead of being scalar values, are intervals, are elements of interval data. And we try to replicate the most common methods and functions used in data frames for this object. We also have some utilities for creating interval data for microdata, and creating intervals either by the standard of making the lower limit of the interval equal to the minimum observed value and the upper limit equal to the largest observed value. Sometimes one may want to make a more robust aggregation, and instead of creating an interval from the minimum to maximum, might want to make an aggregation discarding the lowest 1% and the highest 1%, or the lowest 5% and the largest 5%. So there is also a possibility of making an aggregation based on quantiles defined by the user. The package then includes several methods for the analysis: maximum likelihood estimation of the types of models based on the types of models that will be considered, robust methods for estimation, methods for outlier detection, and in the second part of the course, we'll talk also about analysis of variance and multivariate analysis of variance for interval data, as well as discriminant analysis and model-based clustering. The package is described in more detail in this reference: main data, modeling and analyzing interval data in R, published in the R journal in 2021. In this particular course, we will use for illustration a data set that was created for, that we call flights, that was created for a very famous R data set, NYC Flights 13, which we'll call the microdata dataset, which describes on-time data for flights departing New York City in 2015. The original microdata consists in more than 3,000 flights and 19 variables. For this analysis, we are going to consider of units of interest, the crossing of the flight company with the month of the flight. This will be month of Korea. This will be our units of interest in which there will be variability. We are also going only to consider 4 variables, namely the depart delayed, arrival delay, airtime of the flight, and distance of the flight. So, by doing that, we end up having a total of 185 units of interest. The total possible combinations of month with carrier leads to 192 possible combinations, but not all combinations lead to non-degenerate intervals. One key assumption of the methods that we are going to assume is that the upper limit of the interval is always higher than the lower limit of the interval, what we call non-degenerate intervals, and that is a restriction of our methodology. That will be a reasonable assumption on many problems. And in this particular case, imposing that restriction leads to drop 7 of the possible combinations. And a vision of the data set of units of interest is as shown in here. As we have seen before, the intervals of interest are now intervals, and we have the 185 units of interest. I'm going now to move to the R script that we use as script. Is everybody now seeing the R script?
Yes, we are. We can see it.
Thank you. So, as I said before, we are going to rely on the R package main data. So, first of all, we are going to call it in order to use in this particular course. There are 2 ways in which interval data can be created in main data. One is the one that we going to illustrate here, in which we have a data frame of microdata, the individual flights, in which we have for each individual flight, the individual values. And we are going to aggregate these microdata by flight units, which is a factor that describes how the data should be aggregated. So in this case, it corresponds to, as we have seen before, the combination of the month with the company. And each observation of this factor should follow the same order as the row in the microdata. And in this particular case, we are going to use a robust aggregation instead of defining intervals as the minimum and maximum of the units that of the micro observations that corresponds to each unit of interest. We are going to consider intervals between 5% and 95% quantile, which is done by using the argument aggregate criterion, which by default is minimum and maximum, and in this case, it will create the intervals, the aggregation on these values. So we create the eData object by this command. In this case, again, as I said before, not all possible combinations were possible because some of them had a minimum equal to the maximum, a lower limit equal to the upper limit, which our modeling does not allow. In this case, there were 33 units of interest in which that happened, so they will drop it. And if we look at our object, we see that an interval data object has as row the units of interest and as columns the interval variables that are, as one should expect, represented by intervals. And these are the last observations when that happens. Another way to create interval data that we are not going to use in this example, but sometimes it is used, is when we don't use a data frame of microdata, we have the original lower and upper bounds, which will be the case if we have native or interval data. In order to create an interval data object directly from the bounds, one can use the command eData, which has as arguments a data frame with bounds, or alternative with midpoints and log ranges if so desired, but by default lower and upper bound, and then one can define the sequence in which those bounds are presented. If by default lower bound followed by upper bound for one variable, then the same thing for another variable, but can be all lower bounds followed by all upper bounds. One can specify variable names, one can specify observation names, and so on. So these are the two ways of creating eData objects in metadata. Now, there are most of the typical R methods for data frames are available for eData objects, things like enroll, in this case, considering the number of units, and call, considering the number of interval variables. There is also a plot object, which by default will make a representation of this type. And notice that here I'm also using the indexing, which can, as in data frames, can use numeric index to recognize the different columns or names of these columns. In this case, I'm just looking for the variable distance versus the variable delay on arrivals, and a plot of two interval variables. We have this aspect. As an alternative, one can have also a representation based on rectangles, which will be something like this. Typically, the first one is not, it's easier to understand, but these two alternatives are available.
So these are the counterparts of the classical scatter plots of real data. Now, because we have intervals, there is variability that did not exist in classical data. Instead of single points, we have for each unit and two variables a crossing or else a rectangle, showing the variability in both variables for each unit. Okay. So now that we have seen how to build interval data and how to use it, let's see how we can analyze it. And in fact, most existing methods, at least until some time ago, for the analysis of interval data relied on non-parametric descriptive approaches. Our goal with this proposal has been to have some framework that would allow for parametric inference methodologies. And for this, we introduced probabilistical models adapted to interval-valid variables. So, as mentioned, for each unit, Si, the value of the interval-valid variable y is an interval, usually defined by the lower and the upper bounds. But in fact, for modeling purposes, it's usually preferable to have the equivalent parameterization, which corresponds to represent the interval by its midpoint and its range. Look here at another example, which is the price of cars, and in fact for car models, the price in thousands of euros for different car models. And we see that, of course, the price of the different models varies according to the specific characteristics that one chooses or the stand where you go to buy it. And for some models, this varies a lot, like for the Mercedes here. And for some models, like the Punto or the Corsa, the price does not vary much. Each interval of price can be described, of course, by the midpoint of the corresponding intervals. But we will all agree that this is not enough. It does not tell the full story. And in particular, it does not allow to distinguish cases like here the Honda NSK or the Mercedes SL, which has quite similar midpoints, but very different situation. The price of the Mercedes varies a lot, whereas the price for the Honda is almost fixed, almost constant. So we also need to take the range alongside with the midpoint to describe each interval. The first proposed model is the so-called Gaussian model. And this consists in assuming that the joint distribution of the midpoints and the logs of the ranges is multivariate normal. It is, if we call R star the log of the range of each interval, then we shall assume that the joint distribution of midpoints and log ranges follows a multivariate normal distribution, usually defined by a mean vector and a variance-covariance matrix. If P was the number of interval-valid variables, the number of columns in our interval matrix, we now have a multivariate distribution of size of dimension 2P, because for each interval we take two indicators, the midpoint and the log range. So the mean vector will be maybe decomposed in two parts. The mean vector corresponding to the midpoints and the mean vector corresponding to the log ranges. And the variance-covariance matrix can be organized in four blocks. One that compares midpoints with midpoints, one that compares log ranges to log ranges, and the two of diagonal blocks that compare midpoints with log ranges. Of course, the mean vector is 2p-dimensional, formed by two parts of p-dimensional column vectors of the mean values of midpoints and log ranges, and the four blocks of the variance-covariance matrix are all of dimension p times p, where p was the number of original interval valid variables. The advantage of this model is, of course, that it allows for straightforward application of classical inference methods. With a Gaussian model, we are back home somehow. Does it make sense? Well, we think so. The intervals midpoints act somehow as location indicators. Assuming a joint normal distribution corresponds to the usual Gaussian assumption so often used in multivariate data analysis. The log transformation of the ranges allows coping with their limited domain because, of course, ranges cannot be negative. We'll notice that this model implies that the marginal distributions of the midpoints are normals, the marginal distributions of the ranges are log normals, and because of this, it implies a specific relation between the mean, the variance, and the skewness of the ranges. To generalize a bit more and not just rely on Gaussian distributions, we have also proposed the second model, which considers not the Gaussian but the skew-normal model. And this consists in assuming, again, that the joint distribution of the midpoints and the logs of the ranges now follows a skew-normal distribution, which has three parameters. For those who are not so acquainted with distribution proposed by Azzalini in 1985, we'll just say that it generalizes the Gaussian by introducing an additional shape parameter that allows somehow, in some limited way, to model the skewness. Still, it preserves some of the mathematical properties of the Gaussian, in particular the fact that quadratic forms follow chi-square distributions, approximately. An alternative parameterization is available that was proposed later on in terms of the traditional moments, the mean vectored variance-covariance matrix and the skewness coefficient. Univariate skew-normal distributions look like this. Of course, when the shape parameter alpha is 0, here in pink, we get the Gaussian distribution, the usual bell-shaped. For different values of alpha, we have different levels of the skewness, right or left skewness, leading to different skew-normal univariate distributions here in different colors, blue, light blue and green for negative alphas, and yellow and dark blue for positive values of alpha. A multivariate skew-normal distribution is defined in terms of the density of a p-dimensional standard Gaussian and the distribution function of a standard normal variable. And it is represented in this form. So we have proposed models for interval data. And at this point, you may be saying, well, you kept saying that we should take variability into account and that the data are now different. They do not look like the original data, the classical data, where we have one value per unit and per variable. And now you just code the intervals in terms of classical variables, the midpoints and the ranges of log ranges. Well, this is true, but let's not forget that the midpoint and the range of the value of an interval valid variable are quantities related to one and only variable, and therefore should not be considered separately. Midpoints and ranges for the same variable are not two independent variables. Therefore, the relation between them should be somehow taken into account. We do this by considering different parameterizations of the global covariance matrix. This parameterization will allow taking into account the link that may exist between midpoints and log ranges of the same or different variables. In the most general formulation, we allow for non-zero correlations among all midpoints on long ranges. But we also considered other cases of interest, and namely, that the interval-valued variables are not correlated, but that for each one, the midpoint may still be correlated with the corresponding log range, and this is often the case, by the way. Or alternatively, that midpoints and the respective log ranges of different variables may be correlated, while there is no correlation between midpoints and log ranges. This leads to 4 different configurations for the variance-covariance matrix, where from the non-restricted one, where everything may be correlated to everything, to the completely diagonal variance-covariance matrix, where nothing is correlated and the matrix is just diagonal, to the 2 intermediate configurations which are adapted to interval-valued variables. When the interval variables are not correlated, but the midpoints can be correlated with the corresponding log ranges. Here, the 4 blocks of the sigma matrix are diagonal, or when midpoints cannot be correlated with log ranges and the off-diagonal blocks are null, as it is represented here. The full configuration, no restrictions. The diagonal one, nothing is correlated. Here, variables, interval-valued variables are independent, but midpoints can still be correlated with log ranges. And here, midpoints are only correlated with log ranges, and with midpoints, and log ranges are only correlated with log ranges. We'll notice that all cases are particular situations of the non-restricted configuration 1, and of course, cases 2 and 3 are special cases of 1. And configuration 4 is a particular case of all of them, naturally. But importantly, in these restricted cases, 2, 3, and 4, the variance-covariance matrix sigma can be written as a block diagonal matrix, after possibly a rearranging of rows and columns. In configuration 2, after rearranging rows and columns, we'll have P 2 by 2 blocks. In configuration 2, this is already in terms of 2 P times P blocks. And in configuration 4, this is diagonal in the special case of a block diagonal matrix of blocks of dimension 1, which are single real elements. This block structure is crucial for the next step, which is, of course, the maximum likelihood estimation of the parameters. Once we have introduced models, it's now important to estimate the corresponding parameters from the data. And the first way to address this problem is, of course, via maximum likelihood estimation. Let's first address the Gaussian model. For all configurations, the log likelihood can be written as usually in this form, which depends on the mean vector mu, the global mean vector mu, the sample mean vector x bar, the variance-covariance matrix sigma, and the matrix of squares and cross products of the observed E. Because sigma, the inverse of the variance-covariance matrix, is symmetric, positive, definite, it follows that the maximum likelihood estimation for the mean vector mu is always the sample mean vector x bar. And therefore, the maximization of the likelihood function with respect to sigma reduces to maximizing something with this simplified form. In configurations 2, 3, and 4, which are our restricted configurations, still sigma can be written as a block diagonal matrix, as we said, after a possible rearrangement and rows and columns. And therefore, well-known results allow saying that the maximum of the log likelihood can be obtained by separately maximizing with respect to each block. And therefore, we have closed forms for the maximum likelihood estimates, and this is a classical problem. So we know how to estimate the parameters in the Gaussian model for all 4 configurations of the variance-covariance matrix. In the case of the skew normal model, the problem is a little bit more difficult. The log likelihood of a p-dimensional skew normal distribution looks like this. This is a bit complicated, and here reparametrized by V, which is written here, and eta 0. The configuration 1 is the non-restricted one, and for this case, the problem had already been solved by Azzalini and Capitano by reparametrizing the log likelihood in this way, written here, and then maximizing directly. But for the other configurations, the restricted configurations 2, 3, and 4, we have to numerically get estimates. In this case, we reparameterize the log likelihoods of distribution and log likelihood in terms of the usual moments, and then maximize numerically the log likelihood using as arguments the free elements of these vectors and matrices. Free elements because in the restricted configurations we are imposing that some of them are null, of course subject to admissibility restrictions. All this work had already been obtained some time ago, and you can find it in this paper in Journal of Applied Statistics. And now we go back to the package, to the R script, to proceed to the maximum likelihood estimation in our application. First, before this.
Just before proceeding to the maximum likelihood estimation, let me just show that in the example we have been describing, in the case of the flights data, we have for many variables that the midpoints at the log ranges are positively correlated in, which is usually the case in most cases of interval data. That can be seen in this plot. This is a classical R plot, but also notice that having an interval data object, one can get back the midpoints as a data frame simply by using the command midpoints and then as the argument the interval objects, and one can get the log ranges equally using the command log ranges and the name of the interval data object. This will extract data frames with midpoints and log ranges, and the names of these classical variables, it will be given by the name of the original interval variables, followed by a dot midpoint, mid-p in the case of midpoints, and a dot followed by log r in the case of log ranges. So that's what was used to create a classical R plot relating, in this case, the midpoints and log ranges for the variable arrival delays. And one can see, as it is typical for many interval variables, that there is a strong positive correlation between midpoints and log ranges. After this observation, then I will talk about maximum likelihood estimation in mean data. Maximum likelihood estimation, it is performed by the command MLE, and the arguments for the MLE method are naturally an interval data object, which is the first argument, and then one specifies which type of model might be considered. By default, MLE only considers the Gaussian models. One reason for that is that for problems with a very large number of interval variables, which is not the case of this example, the maximum likelihood estimation of the skew normal model might be computationally demanding. And if one has, let's say, 10 or more interval variables, if one tries to make the maximum likelihood estimation of the skew normal model, since this is done by numeric optimization, that might not be obtained on the fly. and that will be recommended when an R script is used on a batch mode, when somebody asks the R script and then waits for some time until gets the results, but not for online analysis. For problems with a smaller number of interval variables, that is not a problem, and one can get the results for both the Gaussian, which is always fast, as well as the skew normal. So in this case, we are not going to use to default, and we are going to try maximum estimation using both the Gaussian and the skew normal model. And there is another argument for actually all the methods in main data package, which is one can specify the covariance configurations that one is interested. That is given by the value cov case, and by default, main data tries all possible configurations and then returns the model, in this case, the combination of covariance configuration and normal or skew normal model, which is best according to an appropriate criterion. And the choices for criterion are the Bayesian information criterion, which is chosen by default, or one can use also archaic information criteria if that is specified on that argument. In this case, we are going to use the default, so we are going to try to estimate the model for all combinations of the covariance cases and both the Gaussian and skew normal, and are going to select the particular combination which has the minimum value of the Bayesian information criterion, which can be done by using this command. It takes some time because of the numeric estimation of the skew normal model, but that is not a big problem in this particular case. And one thing that main data tries to do is, in addition to finding the point estimates, it also tries to find standard errors of all those estimates. And in particular, not only the standard errors, but the variance-covariance matrix of all the parameters, which, as it is usually the case in R, is returned by the command vcov. Standard errors can be recovered by the command SE, as it is usually in R. In the case of the Gaussian model, that is straightforward. There are known formula for the variance-covariance matrix of estimators of a multivariate Gaussian model. Since our case, we are dealing with Gaussian models with some restrictions on the covariance of some variables. The usual formulas for the variance covariance on the cases that are not restricted are the same. For the skew normal model, what we'll do is to rely on the observed fish information. Now, that sometimes might create some problems, because the numeric estimation of Fisher information in multivariate problems sometimes works well, and in that case, one can get the standard errors by the usual formula. Sometimes there might be numerical problems, in particular, the observed information matrix might be not well conditioned, might be close to singularity. That is a common problem, not only in this particular case, but in general analysis of multivariate models. And that's what happened in this case. We got the estimates, but we are not able to get a non-singular observed Fisher information matrix for this estimation. That's why we got the warning message. The information matrix is not positive definite, which means that in this case we will not be able to get the standard errors of the estimates when using the skew normal model. The results of the estimation are summarized here. So one sees that first for the Gaussian models, then from skew models, the log likelihoods and the comparison criterion, which in this case is the BIC, and in this particular case, the minimum BIC is the most general model, is skew normal model without restrictions of the variance covariances. So it will be, remember that we have a relatively large data set. When we have a large data set, usually general models are more likely than when we have small data sets. So this will be the model that was estimated, and one can inspect the estimates of the model by using the common mean for the mean estimates. If they are, a mean delay time around 38 minutes, an estimated arrival delay of about 28 minutes, and so on, one can get the standard deviations, the estimations of standard deviations, as usual by the command SD. One can get the full variance covariance of the variables by the command var, and the correlations by the command core, and the command coef gives a list with all relevant parameters, in particularly the skewness coefficient, which is important in this case, since the selected model was a skew normal model. And one can see here that for some variables there is not much skewness. However, for the airtime midpoint, and the distance midpoint, and the distance log range, there is some skewness, which is in the origin of the selection of the skew normal model instead of the Gaussian. In this case, we cannot get standard errors for the reasons I said before. If we're using just a Gaussian model, or if the estimation of sufficient information, there are no numerical problems, when we can use also the SE. One could also use the standard error command. Now we'll move to the topic of robust estimate. Yes.
We should notice that we had 4 interval valid variables to start with: the delays on departure and arrival, the airtime and distance. But because we parameterized each one by both midpoint and log range, our variance covariance matrix is now an 8 times 8 matrix.
Yes.
Okay, not 4 times 4, but 8 times 8. And accordingly, the mean vector is an 8-dimensional mean vector, the same for the vector of the skewness coefficients.
Okay. Let's now move on to the problem of robust estimation and outlier detection. And outliers may happen in a data set for several reasons. One may have outliers on individual variables, which are usually easier to detect. One might have outliers because the relations between, even though there are no outliers in individual variables, the relations between those variables for those particular points are not the same as in the common observations, which is usually a type of deviation for norm that are more hard to detect. In the example of the different car models, we can see here that in terms of the engine capacity of Honda SQ and Porsche, there are no outliers, neither according to the midpoints, neither according to the log ranges, but there are outliers because the relation between midpoints and log ranges, it's not the same as the remaining variables. And for these types of problems, one needs a multivariate method of outlier detection. Typically, the classical methods of outlier detection are based on Mahalanobis distance measures, and they are designed in a way that they are able to look to outliers that are created by different relations about variables. However, in order to identify outliers, one typically does not use the classical Mahalanobis distance, because the classical Mahalanobis distance are affected by the outliers themselves, what it is known as masking. If you look at this problem, we have here most of the data, there are some outliers, and one can look at the data that are within a certain distance of the center according to the classical Mahalanobis distance, and these ellipses are much larger than what it is defined by the common observations, because the estimations of means and variances were affected by the outliers themselves, which enlarges the ellipses. That's the problem of masking. To avoid that problem, one must use robust estimates of means and variance and covariance to find Mahalanobis distance that excludes the outliers. And that is typically done by iterative methods. I'll go back here just to complete the idea that it is done by iterative methods, usually what it is called trimmed likelihood estimators, in which we estimate the quantities of interest, removing the observations which have values that are atypical, very unlikely to occur, and that it is typically done by an iterative procedure, but that is the main idea. And that is what it is done typically on multivariate outlier detection in classical statistics. So, as we said before, we represent interval data by midpoints and log ranges possible, we restrict, and then we adapt the classical outlier detection to the data, to this representation, always looking at the possible restrictions of the variance covariance matrix according to the parameterizations that we consider for interval data. After that, robust Mahalanobis distance may be computed. We also implement some non-refinements of the classical robust and outlier detection methods for classical data. I'm not going to get into much details here because that is a little bit too technical, and for the people we want to use those methods, we have several parameters that can control many of the choices that are done in robust methods and outlier detection, but we set the default values to reasonable choices. So the user who is not a specialist in outlier and robust methods usually can use our package using the defaults. The user who has a deeper understanding and wants to play around with different alternatives can also do that by playing around with the methods for detection. So in essence, we have two procedures for robust estimation, one called full TLE, which does an exact search of trimmed maximum likelihood, and that will be recommended when we have relatively small number of observations, because a full search of trimmed likelihood is computationally very demanding and can be done with 10, 20, let's say up to 50 observations, but more than that becomes intractable. And for larger problems, we have fast TLE, which is an adaptation of a very common method for robust estimation. Just to give you an idea of the options available, I'm going to use the full TLE, but fast TLE are essentially the same. We have, as usual, the interval data object, the covariance case, selection criteria, and then many choices that relate to the details of the robust estimation. In this example, we are just going to use fast TLE with the defaults, and the summary In this case, for robust estimation, we are only using the Gaussian models. We have not implemented robust and outlier detection for skew normal. So in this case, there we are comparing only the 4 configurations for the Gaussian model. Again, the chosen model was the unrestricted case, and one can get the mean, standard deviation, and the correlation by the usual comments. After one gets robust estimates, one can get the outliers using another command, get data outliers, which uses as arguments the data frame with the interval data and the object with the robust estimates that we just computed before. One can print the outliers, or one can make a graph in which they are identified. In this case, we have many outliers. In this case, we have many outliers, but they follow a similar pattern. They are most of the observations for the carriers FL, or VX. So it seems that these two carriers have some characteristics that deviate from the usual pattern.
Okay, don't know if everybody got it, that once the robust Mahalanobis distances are obtained from the robust estimates, the outliers are identified as observations that fall after, that are larger than quantiles of appropriate distribution.
Yes.
Okay. Which, given that we assume a multivariate Gaussian distribution for the vectors of midpoints and log ranges, will be either classical chi-square asymptotic or approximations, or appropriate alpha and beta finite sample approximations for smaller data sets. Okay, so all this is, as Pedro has mentioned, parameterized in the option in the package that, so if we just look there. So by default, we have the chi-square quantiles to identify outliers. Otherwise,
Help.
it was in the help. Otherwise, there are the alternatives of the adjustments and beta distributions and so on for small data sets. By default, not too small data sets, the chi-square usual approximation that is used currently for multivariate outlier identification is used. Okay, so here we are. So this is the end of part 1, where we have introduced symbolic data analysis. We have talked about the models. We have introduced the different types of symbolic variables, and then we have addressed the modeling of interval valued data, proposing 2 probabilistic models for interval data, one based on the Gaussian distribution and the more general one based on the skew normal distribution, for which then we developed maximum likelihood estimation, as well as robust estimation in case of the Gaussian and corresponding outlier detection procedure. In the second part of the course, we'll now proceed to multivariate data analysis methodologies. But here we will make a break as initially planned. But we can ask if anyone has any question at this point. Please feel free to...
Yes, thank you very much for that first part. It was great. We have several thank you messages in the chat. We have a couple of questions. I would like to share them with you now. and then we make the break. Is that okay?
Yeah, perfect.
So the first one is from Lilia. Lilia is my colleague here at the Department of Statistics, and she's talking about interval time series, for instance. Considering the interval of the number of new cases of COVID in all cities by week, is it possible to use this package, the package that you were presenting?
For time
Time
series?
series.
No.
Yes, time series.
No, the package only analyzes cross-sectional data. Still, there are some works already developed for the modeling or the analysis of interval-valued time series, both by us together with other people or other people, including in Brazil, but not only. So there is already work developed for the analysis of interval time series, but it's not what here today we are talking about, and not with this package.
Yes. Okay. Thank you. And there is another question. Actually, this is more like a comment. Why did you use the flight data from 2013 and not the more recent data? I guess it's because it is just an example, an illustration, and not exactly an application.
Sure, and it's a data set that is already available in some R packages. It is well known, so it was easy to import it from other
It is an illustration. We just wanted to use a classical data set that is well known to illustrate the idea. It was not our interest was not the analysis of that particular data. It was illustrate the methods. And since it was a classical data that has been known by many people and it was available on R, we just used that as a simple example.
Yes, indeed. And the last one is also for Nadiana Bassi. Sorry for the pronunciation. Is on why do you have to use log for the range values and not just the midpoints and range? This is what we were talking about like 10 minutes ago or so.
The reason is because the ranges have a limited domain because they cannot be negative at all. So it did not make sense for us to model them as Gaussian or even skew normal, okay? And we wanted to have some multidimensional joint distribution to proceed. Whereas when we take the logs of the ranges, then they can be, of course, positive and negative, and we can have joint Gaussian or log normal or skew normal distributions. This has to do with the limited domain of the ranges. Of course, we could consider other distributions for the ranges, but then the modeling of having Gaussians for the midpoints and something else like gammas for the ranges would complicate the modeling and the estimation to proceed.
I think it is more or less known that the multivariate analysis based on other distributions other than the Gaussian is not as well developed and not
straightforward.
Not as straightforward, and not developed for many other things. They are just not methods for most of the analysis that are currently done. There might be some specialized work, but it's not widely available. So we just thought that having something that could be modeled as Gaussian was really worth it. That was our rationale for doing that.
Okay, perfect. Those are the questions that we have for now. In the break, we share the slides and the code. Maybe in the break, the people can have some further questions, and we can ask
so
when
we start, we can restart with another round of questions if there are some. We continue.
So now we'll have about between 10 and 15 minutes break. We'll have the countdown when we start again. So in about 10 minutes, we will be back. Thank you, Paul and Pedro. Have a break. You deserve it. Thank you.
Thank you very much. Thank you.
Lugares são como pessoas. Tem aqueles que apenas passam por nossa vida e aqueles que deixam a sua marca. Tem aqueles sem graça e aqueles instigantes. Lugares são como pessoas. Tem lugar que tem um incrível poder de dar um clique na nossa alma. E quando a gente vê, já entrou no nosso coração e ele está ali, instalado. Salvador é assim. Uma festa para os sentidos. O gosto do dendê fica na boca, quase como uma tatuagem no paladar. O cheiro do mar não se contenta em ser sentido. O sal gruda no corpo e quer se misturar com o nosso suor. As imagens são tão carregadas de sentido que parecem ter sempre algo novo para lhe mostrar, mesmo que você já tenha visto dezenas de vezes. E a batida? Será que é por acaso que tem o mesmo nome daquilo que lá no peito faz a gente se sentir vivo? Uma cidade que é dividida em duas partes e ligada por um elevador não nasceu mesmo para ser convencional. Aqui, o palco anda. E o mais impressionante, o povo sai andando atrás. Aqui o banho pode ser de mar, mas se preferir, pode ser de pipoca também. É o coração da África, o berço do Brasil e tem o sorriso que é do tamanho do mundo. Só quem nasceu de uma mistura pode juntar tão bem coisas tão diferentes. Salvador tem um santo do candomblé para cada dia da semana e uma igreja para cada dia do ano. Salvador é superlativa, generosa, bem-humorada e de bem com a vida. Não dá para ser o mesmo depois de conhecê-la. Não dá para ser igual depois de sentir suas sensações. Não dá para ser igual depois de perceber suas singularidades. Não dá para ser igual depois de sentir seus cheiros, ouvir seus sons, provar seus sabores. Não dá para ser igual depois de ouvir suas histórias. Não dá para ser igual depois de conhecer um lugar tão surpreendentemente diferente. Salvador, você sente que é diferente.
Boa, good afternoon. I was about to start to speak in Portuguese. Good afternoon. Your microphone is muted, Paul.
I guess they are not just Lusophones online.
Yes, exactly. I'm sure they are not. So in the break, I hope you had time to breathe a little bit. There were no questions in the chat during the break, so I think we can move forward for your second part of your talk. If you can share your screen, I can put it on in here. So we'll have about between 1 hour and 1 hour 10 before we finish. So please control the time as you wish. We can leave like 5 or 10 minutes in the end for possible questions. So just to organize as you feel more appropriate.
This should be another 3 series of methods and the script.
Yeah. Okay, perfect. So please go ahead.
Okay. So we proceed here. So welcome back, everybody. And as promised, now we proceed to methods for multivariate analysis of interval data based on the models that we have introduced in the first part. And as before, we shall be first introducing the methods and here and with some small example, and then move to the package and continue the analysis of the flights data applying the corresponding methods. So first, we'll address analysis of variance for interval valid variables, then discriminant analysis, and finally, model-based clustering. We'll just finish in the end by introducing you to the main references in symbolic data analysis. So let's look at the analysis of variance. And I'll first recall the main objectives is of ANOVA and MANOVA. I'm sure people know well about this, but just to fix vocabulary, and if there are people who do not have it present in their mind, let's just recall that analysis of variance allows for the comparison of means of one or more numerical variables in 2 or more populations from which random samples were drawn. For example, when we want to compare the mean value of the sales of some given product in different shops. So if we have K shops, which here would be the levels of the factor, the shop, for each shop we have a random sample of the value of the sales observed on different days. The null hypothesis of the test is that the population mean values are all equal across the factor levels, so across the different shops, against the alternative that are at least 2 populations of those compared that have different mean values. The ANOVA, in fact, performs the test by comparing the variance within the samples, within the groups, also called the residual variance, that is measured by the sums of squares of the quadratic deviations of each observation to the local mean, the mean within the sample, with the variance between the samples, the groups, that is supposedly explained by the factor, in the example, the shop, and it is measured by the sums of the squares of the difference between each local mean, the mean for each shop, and the global mean. If the residual variance, the local variation, is very low as compared to the explained variance explained by the factor or between levels due to the factor, we then may conclude that the mean values of the variable and the study are different between the groups, and we reject the null hypothesis. When there is more than one variable to be compared, those mean values we want to compare. In the multivariate setup, we have P descriptive variables, and for each of which we have one sample for each level of the factor, then the data can be organized like this. For each factor level, say for each shop, we have a random sample for each of the variables and the study. Then we are in the case of a multivariate analysis of variance, and the test proceeds by comparing now the determinant of the within groups matrix, written here, matrix W, with the determinant of the global matrix T, which compares each observation to the global mean vector. Notice that now each individual observation, as well as the local mean vectors and the global mean, are p-dimensional vectors if p is the number of variables in the study. So back to our interval valid variables, now that we have set up the vocabulary. We have established that each interval valid variable, y, is modeled by a pair composed by a midpoint and a log range. That is, the analysis of variance of one variable y is always a two-dimensional maneuver, a two-dimensional multivariate analysis of variance of the couple midpoint log range. Of course, the simultaneous analysis of all interval valid variable y may be accomplished by a 2 times p dimensional maneuver following the same procedure. And this has been implemented and may be applied both in the case of Gaussian or the skew normal model that we have introduced. Let's first start by the particular case when you have a Gaussian homoscedastic situation. Then for one interval valid variable, the Wilks lambda is defined, as we all know, as the ratio between the determinant of the within matrix W to the determinant of the total matrix T, which can also be written in terms of the E matrix, so the sums of squares and cross products matrix, both for the determinant for the alternative hypothesis divided by the null, where each of them are 2 by 2 matrices corresponding to midpoint and log range of this one interval valid variable. A null hypothesis, of course, corresponds to the situation when we are considering that the means are equal across groups, and alternative when the means are different. This corresponds to, we also can use the likelihood ratio statistics, the log likelihood, the ratio of log likelihood in the null to the alternative hypothesis, which can be written in terms of the Wilks lambda in this particular case of Gaussian homoscedastic. In the general case, we shall rely on the likelihood ratio approach, where we maximize the log likelihood for the null hypothesis, the mean for the Gaussian model, or the location vectors for the skew normal are equal across groups, and the alternative hypothesis when they are different. At least 2 of them are different. L null and L out are here the maximum log likelihoods under the null and alternative hypothesis. In all cases, that is, for both the Gaussian skew normal distributions and all configurations of the Gaussian of the variance covariance matrix, as usual, -2 logarithm of lambda follows asymptotically a chi-square distribution, which will allow to perform the test. To see how well it works, we have performed the simulation study. This has shown that when sample sizes are not too small, the tests do have good power, and the true significance level approaches nominal levels when the constraints assumed for the model, that is, the constraints of the variance covariance matrix or the type of the model, are indeed respected. We also notice that the method assuming that the data is normal with the non-restricted configuration 1 never performs worse than any other method when data is indeed normal. Furthermore, the skew normal model requires large samples. Let's see an example of application. And here this data set, also available together with the package, concerns temperatures measured in meteorological stations in northern China. The data consists in the intervals of observed temperatures in the Celsius scale in each of the 4 quarters, that is January to March, April to June, July to September, and October to December, from 1974 to 1988 in 22 stations, as written here. The full data table comprises 330 rows and for columns, 1 for each quarter. In fact, the 22 meteorological stations belong to 3 different regions, the north, northwest, or northeast of China. MANOVA has been performed to assess whether the 3 regions were different as concerns the temperature measured in the 4 quarters. We have applied, considering all alternatives, that is both the normal and the skew normal, for all 4 alternative configurations of the variance-covariance matrix. The best fit was for the most general model, skew normal model with non-restrictive configuration 1. However, whatever the configuration, the p-value was always very small, showing that the regions were indeed different in terms of the mean values of the interval value temperatures. And this is it. We now move to the package to see this in practice.
So we are going to illustrate this procedure using the data that we have been discussing before, but since we have identified some outliers in the previous analysis, actually we are going to do the maneuver in the typical data, in the data excluding the outliers. Notice that one can use the indexing, of interval data objects in the same way as one does with regular data frames. For instance, after having identified the outliers by the previous comments, and we got an object called flights outliers which actually it is not just outliers because it also has some information regarding the robust Mahalanobis distances. Sorry. The structure of an object with 5 outliers has a field called outliers with the outliers themselves, and it has another field, MDA, which saves the Mahalanobis distance for each observation, and then some other information regarding the types of parameters that were used in the robust estimation and outlier detection. In our case, it was the default values, but that was retired. So in order to get an index of the outliers, one needs to call the field outliers from the object that was returned for get data outlier. And after getting a vector with those values, one can simply eliminate that from an data object by, as is usually in R, using a minus and that vector. It will drop all the rows corresponding to these observations for the analysis. We are going to do a maneuver, distinguish what we'll call regional carriers from main carriers, which in our case we have 4 regional carriers, which are 9E, EV, MT, OO, and IV. So first we do some standard R programming to get a factor that distinguishes the regional carriers from the main ones. This has nothing to do with package. This is just some R programming to get a factor describing the groups in our particular example, and the maneuver itself is conducted in main data by the command maneuver in caps. And the arguments of maneuver is again the eData object with data, a factor that describes the classes, which it is called grouping, in our case, the factor that we have just created, and then again, one can choose the model. By default, you try only normal models, but one can say only skew normal or normal skew normal. The covariance configuration that one may choose, and we are actually conducting kind of a generalized maneuver, because traditional maneuver, it is based on the assumption of equal variance covariance across groups, and usually a constant assumption. We already consider different models. We call the assumption of equal variance covariance matrix in the case of the Gaussian model, or the equivalent measures in the case of skew-normal models. Now, in the case of the Gaussian models, we consider homogeneity, homodacity. In the case of skew-normal, we call a location model, and we also have an option of making a test to compare the means, admitting that the covariance may be different across groups, what we call heterogeneity, or the most general model, in which you assume a skew-normal model, and all the dispersion and association measures that are assumed in skew-normal model may all be different. That is general. By default, it is the classical case, Gaussian with a normal stochastic assumption, but these variants can be also used. And these are the most important arguments of this particular method. In this case, we are going to try normal and skew-normal models. We'll try all them, but we are going to assume a normal stochastic assumption. We are not going to allow for, as it is usually in classical maneuver, that variance covariance differ across groups. So doing that, one should execute this program, this command. So the eData object that you're going to analyze excluding the outliers, the factor describing the groups, and the models that we are going to compare. And notice that this is going to make, in the case of skew-normal, numeric optimizations for all the groups, for all the variance covariance configurations. That's why this is a little bit more slower than even the maximum likelihood estimation. Nevertheless, for a problem with 4 interval variables, it's still not too much. In a couple of seconds, we should get results. Maybe not a couple, but, but not a couple of minutes. Eu defini os grupos, não defini?
Defini. Não tenho certeza. Não. Não definiste, porque estão aqui. Acho.
E defini os outliers.
Pois não sei. No.
I think I forgot one step. That's why it's taking so long. It should not take this long. I'm sorry. But I think I forgot to run this command in which I correct the outliers in this vector. I believe that was the problem. So first I need to do this. Let me define the groups once again. And
now we wait again.
hopefully now it will take too long. I think I forgot to run the comment in which defined the vector with the outlier values.
Takes a bit.
But now,
It always takes a while, not always the same length of time due to numerical optimization that it's behind for the skew normal distribution.
Paul and Pedro, while we wait, maybe I can share with you one question.
Yeah, sure.
Yeah, sure.
So-
Welcome.
The question it came right after you start. It is from your slide 47. If you can go to your slides, it will be in slide 47.
Slide 47.
I will read it for you.
I go to slide 47 here.
The question is from Nilario. It says the x and y axis are respectively all the midpoints and log ranges from every variable. The partial
Here
delay.
in this slide?
Yes, it seems so. 47. And then is asking that they are the midpoints and log ranges for every variable together, or only one of them. I think.
Well,
the Mahalanobis distance is computed from all the midpoints of all the log ranges of all the variables. This is just an illustration of two variables to show what the problems with Mahalanobis distance in the case of two variables. But in the implementation, we consider all 2 times p variables to compute the Mahalanobis distance.
that is 8.
In the
2
example.
times
Yes.
the 4. Okay, this is just an illustration to get the concept of the robust estimates and why they are important.
Yes. Okay. Perfect. Thank you very much.
This is done. Finish.
Right. Okay. Please go ahead.
Yeah.
So finally, remember that this time we have to have the numeric optimization for all groups. That's why it took a little bit more than the other cases. And the results are like this. So one has for the null model, in this case, for the model in which we assume that all the means, in this case, the means of midpoints and the means of the log ranges are equal across groups. And the same thing for the full model, in which the means might be different. And then again, we have log likelihoods and for combinations of Gaussian models and skew normals for all combinations tried, and then our comparison criterion for solidity in the model, which is BIC, the Bayesian information criterion, which then again, we have a relatively large data set. It then again chooses the most general model, the skew normal with the unrestricted configuration. And based on this model, then we can look at the chi-square test statistic, but one could compute the other ones if so desired. And in this case, there is no doubt whatsoever that there is indeed some difference between those variables between the regional and the main carriers. You can see that p-value is essentially 0. After seeing that there is a difference in at least one of the variables, one might proceed in trying to find out for each particular variables there will be differences. In this example, it turns out that there are differences in all 4 variables. Here we are illustrating the maneuver using first the delay on departures, and then again we just select the variable delay on departures by, in this case, the name of the corresponding interval variable. One can use also an index with its position. And this should be a little bit faster because one is using just one interval variable. But it still takes sometimes every time numeric optimization of skew normals are involved. And you can see, well, the p-value is not as close to 0 as in the other case. Nevertheless, it is also obvious that the groups are different, and the selected model was again the skew normal. Here it does not, yes, there are only 2 configurations that are relevant. Midpoints are correlated with log ranges or are not, because we are dealing only one variable.
For the arrival.
That's why here one has just configurations 1 and 4. Midpoints are correlated with log ranges and not. And they seem to be correlated. And for the arrival, this was slightly faster. And then again, the groups are also different in terms of arrival delays. They are actually different in terms of 4 values, but so that one can assume the norm for any variable desired.
Yeah. And we stress again that even for individual variables, since each individual variable, interval valid variable, is modeled as a couple, midpoint log range, the procedure is always a maneuver. Okay. So proceeding now to discriminant analysis. And this is just a relatively straightforward extension of classical linear and quadratic discriminant analysis. In the case of the normal model, the Gaussian model, for each configuration of the variance covariance metrics, there are 4 of them, an estimate of the optimum classification rule may be obtained for the corresponding variance covariance metric, and this is direct generalization of classical linear and quadratic discriminant rules, which are indicated here. And we notice the main difference is because in linear discriminant analysis, we assume that the groups are different only in terms of the mean vector, but they have common variance covariance metrics, whereas in quadratic discriminant analysis, the groups are assumed to be different, both in terms of the mean vectors and the variance covariance metrics.
And let me just say that one difference from this process with classical N is that in this case, the estimate of the covariance may be one of the restricted cases.
Yeah. In the case of the skew normal model, we have means, variance covariance, and the shape parameter. So there could be 3 alternatives to be considered. First, that the groups differ only in terms of the mean vector, that differ in terms of both mean vector and variance covariance metrics, or that the groups differ in terms of all parameters. In fact, we have considered only the 2 extreme cases, only the first and third cases, which we call location model. That is, when the groups are assumed to be distinguished only in terms of mean vector, but they have common variance covariance metrics and shape parameter, or the general model when the groups are considered to be different in terms of all parameters. Again, some experimental results from simulation showed that the parametric rules generally outperform distance-based ones that had been proposed in literature before. In homoscedastic problems, as expected, linear discriminant rules perform best. And in large training samples and heteroscedastic condition, quadratic methods are usually superior. Nothing new so far. What is new here? It's that when we have small training samples and the problem is heteroscedastic, restricted quadratic rules are preferable, even in some cases when the model assumed is not true. That is, whereas in classical cases, when you have small training samples, irrespective of the fact that it's heteroscedastic, quadratic rules do not perform well because of the large number of parameters that need to be estimated that do not allow it to perform well. Here, the fact that we use restricted variance-covariance matrices allows to model heteroscedasticity even with small training samples. So we may conclude that the restricted configurations provide a natural way of imposing constraints and are indeed effective in reducing expected error rates, especially in heteroscedastic problems with small or moderate training samples. And this is detailed and with all simulation results in this paper in the Journal of Classification. And before proceeding to the last method, we go back to the package and perform discriminant analysis on the flights dataset.
Okay, now, in terms of the package, we have to perform the discriminant analysis itself, we have three methods. We have LDA to perform linear discriminant analysis, we have KDA to perform quadratic discriminant analysis. These are the same names and methods as in classical R, but these are methods that will recognize when the first argument is an interval data object, it will apply the respective method of our package. And we also have SNDA for skew-normal discriminant analysis with an argument to distinguish the location model for the general model. So if one just wants to find the rule, one simply call the LDA common if one wants to find discriminant analysis with the interval data object and the grouping factor. However, to evaluate a discriminant analysis method, usually it is necessary to perform some sort of cross-validation analysis of error rates. It is well known that the error rates of a linear discriminant rule, error rates computed on the same data that was used to estimate rule tends to be over-optimistic. So in order to have a fair assessment of that rule, one needs to have some way of evaluating error rates in data that was not used in the estimation, what is usually known in statistics as cross-validation, and there are several ways to do that. One of the most famous is leave one out, in which one observation is in turn leave for the estimation and use for using for the derivation of the discriminant rule and use for estimation error rates, and that is repeated for observations, or some sort of key-fold cross-validation in which some simple procedure it is done. In order to help this analysis, we have a special command called DA cross-validation. This is actually quite a general command, can also be used outside the package, and it is a procedure to estimate error rates, which has a first argument, the data, the second argument, the grouping factor, and then the training algorithm. In our case, it will be LDA, KDA, ESDA. And it has also an evaluation algorithm that it has a default that it is just based on error rates that is implied, and it can be used with leave one out if the argument L100 it is true, otherwise it can be used for key-fold cross-validations. And the derivation of the samples in that can be stratified according to the group or not. So this is quite a general tool to help evaluate the performance of a discriminant analysis method. In this case, we are going to compare linear discriminant analysis by leave one out with quadratic discriminant analysis, and also we also have here as comment doing the same thing for skew normal discriminant analysis. This is common because this one would take just too long. Remember that every time a skew normal needs to be applied, there is a numeric optimization that needs to be done. And in this case, since we are using with one out, that will have to be done as many times as the number of units in the data sample. That can be done in the batch job. If somebody does that not online, but running on the background, then after a couple of hours can get results. We did that too for our papers, and usually after we leave to one night running, and the next morning you get results. But here for illustration, I'm just going to run the cross-validation, again excluding the outliers for linear discriminant analysis. And one can see that we have an estimation of error rates of 1.4% for the regular carriers,
for the
main carriers, sorry, a perfect for regional ones, which is a global rate of 0.9%. For the quadratic discriminant analysis, in this particular case, the classes are changed in terms of the one that performs best. In this case, it was the main ones that got perfect results, and the estimate of the error rate, it was twice as much as in the linear discriminant analysis. And in this example, well, I'm not going to do it online, but we also did the same thing for skew normal, both for the location as well for general model, and the results are worse. In this particular example, linear discriminant analysis performed the best. So one can get a linear rule simply by calling LDA, this time with the interval data object and the factor describing the groups, and one can get the predictions by the usual predict R method, actually adapt to these rules, but it is the usual syntax for R with the discriminant rule that we just estimated and the data for which we want to make the prediction. In this case, we will just illustrate in the same data as used for the estimation, but could be an outside some new data if so desired. And one can see the predictions simply by printing the respective object. Again, the object that is returned by the prediction, it is actually a list, because in addition to the prediction themselves, it includes the posterior probabilities, which is also useful information, then again assuming our Gaussian model. So in this case, we just print the classes, but the posterior probabilities are also available as an element of the resulting list.
Okay, and this is it for discriminant analysis. And we proceed to our last method, namely model-based clustering. This will be done only for the Gaussian model. And we briefly recall that what this is, that model-based clustering is based on the finite mixture model, where we assume that our data results from a mixture with weights P times L of different densities, one per group, and identifying the mixture allows identifying the clusters in the group. The mixture is estimated by maximum likelihood, which is applied by maximization of the log likelihood function, as here, for all n observations. This is done with the very well-known expectation maximization EM algorithm. And as usual, trying to avoid local optima, each search of the EM algorithm is replicated from different starting points. The selection of the model and the number of components will be done, as it's often done in such cases, with the BIC criterion, which uses the log likelihood and also penalizes very large models. What we want to stress here is that in standard model-based clustering, the BIC is used just to identify the number of components, that is, the number of clusters. In our case, it will also be used to identify the model, because for each, for the Gaussian model that we are using, we have 4 different possible configurations of the variance-covariance matrix. I recall modeling the relation that might exist or not between midpoints and log ranges. So the BIC will be used to both identify the configuration, that is the specific model that best fits, and together the number of components. And this is it. I mean, otherwise, the method is just a general extension of the standard model-based clustering based on Gaussian distributions. And before proceeding to the package, I will illustrate this with 2 data sets of very different nature. The first one refers to data from the Portuguese labor force survey from the first semester of 2008. And we had 1,540 cases relating to people who were unemployed at the time of the survey. And 2 variables were considered: the activity time in years, so the time that people had worked before being unemployed, and unemployment time in months. This is for how many months were the person already now unemployed. The microdata were gathered, aggregated in terms of gender, region, age group, and education, leading to 58 sociological groups, which are our units of interest, each of which is described by the intervals of activity time and unemployment time. Applying model-based clustering to this data set, the lowest BIC value was observed for a solution in 5 components, that is leading to identifying 5 clusters with an heteroscedastic setup, and modeled by case 2, where the interval valued variables are modeled as independent, and this was the best fit. Here we have, for all cases, the activity time versus the unemployed time. So the crosses scatter plot, which is the counterpart of the usual scatter plot. We know where we can notice that persons with large and widely varying activity time, so that had already worked for a long time before, so not so young people, also tend to have long and varying unemployment times. Whereas people that haven't worked for not so long, so they are in the early days of their professional career, they will be unemployed usually for much shorter times. So here are the 5 components or the 5 clusters and the corresponding mean vectors and variances for the Gaussian distributions associated with each of them. We notice that the clusters are more or less balanced, except that C4 is a little bit smaller, half, and C1 is a bit larger. And we notice that the classes, the clusters, here called usually components, are distinguished both in terms of the midpoints of both the activity time and the unemployment time, and the log ranges, the variation. And for instance, class number C3 and C4, C5 are people who have already worked for a long time and that are unemployed for very, very long time, especially C4, 10% of the groups, people who are unemployed for, on average, the midpoint is 150 months, more than 10 years. And we can see also that the log range is much larger here than in other cases, especially in C2, where people that have worked just for a short time and are not employed for a very long time. Okay, it is heteroscedastic. We notice that both midpoints and log ranges, especially midpoints, have very different variances across the groups. Here is a parallel coordinating plot showing the 5 components, the 5 clusters in terms of activity time, midpoint and log range, unemployment time, midpoint and log range. We shall notice that the scale here, the values, they vary from the minimum and the maximum, overall minimum and maximum of each variable, so that the values from one parallel coordinate cannot be compared with the values of the other. Okay, so the component C4 or cluster 4 in blue here are people who have worked longer, also with longer variation, and are unemployed for a long time with also large variations among them. Whereas component C2 here in this dark greenish color down below, is people who have not worked for long, and this does not vary much, and are not employed since a long time. And this kind of representation allows us to compare the clusters in terms of the different midpoints and log ranges of the different variables. So although the number of observations is relatively low, just some tens, a restricted homoscedastic model has been identified as best fit. And the method shows the best parameters, preferring a heteroscedastic model to a lighter homoscedastic one, and picking up a restricted configuration for the variance-covariance matrix. That is, sparsity was chosen by choosing a restricted model and still modeling heteroscedasticity, rather than by having an homoscedastic model and a full variance-covariance matrix. But we had two restricted configurations. Choosing 2 as opposed to 3 implies that the correlation between the two parts, midpoints and log ranges, was considered more important than the correlation between the two variables, the activity time and unemployment time. And as we have noticed, components can only be separated by considering simultaneously midpoints and log ranges. The other example concerns the meteorologic data from the United States. I think I mentioned this data at the beginning of this course. This data set records temperatures and pluviometry measured in 282 meteorological stations in the USA, and 3 interval-valid variables are considered. The temperature ranges in January and July, so in winter and summer, and the annual pluviometry ranges. In this case, so we have 282 units described by 3 interval-valid variables. The lowest BIC value was observed for an unrestricted heteroscedastic solution with 6 natural clusters, because they correspond to the arid inland west, Alaska, southeast, northeastern, Midwest, Pacific Islands, and Puerto Rico and Pacific coast, as you can see here, where the 282 stations are represented in a graph crossing longitude and latitude, and are colored differently according to the cluster. And we see a cluster corresponding to Pacific Islands and Puerto Rico, one cluster for Alaska, one for the Pacific coast, one for the desert and inland, and then the southeast and the northeast. Quite natural clusters were identified. And here again, the parallel coordinate plot showing that, so cluster in pink is C2, this is Alaska. Of course, cold temperatures and high pluviosity. So here we have midpoints, 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 and then log range, log range, log range. And so medium, not so high variability. The cluster in brown is the Pacific Islands, where you have the highest temperatures and very high pluviosity. It rains a lot, tropical climates, and then not so much variability in the temperatures, but a large variability in the rain. Okay, and we can compare the clusters in this way. So the clusters were differentiated not only by the midpoint, but also for the log range variables as before. Moreover, the clusters displayed highly different variances, and here are some examples. Alaska presents very high variance for the January midpoint, while area inland west and Pacific coast high variances in July, and other particularities. So it is highly heteroscedastic setup. And this stark difference in the variances illustrates the need for an heteroscedastic setup for this data. So in general, the conclusions for the model-based clustering was that the proposed modeling was successfully applied to real data sets of different nature and size. So the official data, not that many units, and this meteorological data, quite a large data set, highly heteroscedastic. Adopting those three restricted configurations, which are adapted to interval data, proved to be an adequate approach because it allowed to model heteroscedasticity and still keeping a somehow sparse model. It was indeed important to consider both the information about position conveyed by the midpoints and the intrinsic variability conveyed by the lower ranges in analyzing this interval data. And we stress the flexibility of the model in identifying heteroscedastic models, even when data sets are not so large. And here is the reference for this work. Okay, so before now going back, we go back to the package to apply model-based clustering to the flights.
And the main comment to apply model-based clustering, it is called eData mQuest, which is somehow based on the mQuest package for classical data. And one can see that when the main arguments are again the eData object with the data, the covariant case that one considers by default all of them and the selection criteria to compare them, the number of clusters that one wants to try. By default, one tries 1 to 9 clusters, but one can increase or decrease according to the particular application. And if one just wants to consider homoscedastic solutions, if one wants to consider just heteroscedastic solutions, or if one wants to consider both of them. So in this case, since we have a large data set, we are actually going to try up to a maximum of 16 clusters, and with both homoscedastic and heteroscedastic solutions, and again, excluding the outliers. So that will be done by running this command. And in order to compare the different models tried, and there are many of them because we have 1 to up to 16 clusters, the different configurations and the 2 different models, it is useful to make a plot that is called plot information criteria, in which one can see what happens with both the homoscedastic as well, which is straight lines, as well as the heteroscedastic, which is the dotted lines, for all the different covariants identified by number and all the different clusters. In this case, it seems that the best result is an homoscedastic an homoscedastic case with 9 clusters and the unrestricted configuration. And there is one thing that I said that it is actually not entirely correct. This is implemented only for Gaussian models, not for
this I had said.
Not for skew models. The option is between homoscedastic and heteroscedastic. One also has some numerical results, which in addition to the best ones, one can see next to best ones and the difference in BIC, because sometimes it's worth not to settle just for the best one, but to explain some alternatives. Now, a summary of the results will give, first and most, the number of observations in each cluster, and if one wants to have the classifications, one can use the argument classification. Actually, By default, the summary just prints the numbers in each class, but one can ask the parameters and classification results by using the corresponding arguments. And in addition to just looking for the best solution, one can also look for any of the other any other solutions, as said before. There is a common for the probabilities, for the proportions of this cluster, mean for the means, then there are ST for standard variance and so on, and a parallel coordinate plot can be created by this command, which shows the similar graph as we have seen before. And one can also look at graphs of other models other than the optimal. In this particular case, in addition to the best heteroscedastic model, one may want to look also at the better heteroscedastic model, because which chooses a restricted configuration, depending, and if one wants to explore the solutions of another model, one simply says model, homoscedastic and heteroscedastic, G the number followed by the number of clusters and the configuration case. And in this case, this might be useful because a solution in this smaller number of clusters might also be interesting. And then again, using these quantities, one may explore the results. Here I'm just describing the functionalities of the method. In this particular case, one cluster is characterized by high values on both the midpoints as well the log ranges of the delay variables, and low values on both the midpoints and log ranges of time and distance. That will be this red cluster. Another cluster on brown, it will be exactly the opposite situation. So low values on midpoints and log ranges on the delay variables, and high values on the airtime and distances. Then it is also interesting to distinguish these two clusters. This one tends to be relatively high, both for delays and distance airtimes, while this one has a similar value for delays, but lower values for airtime and distance. And then again, the results are consistent both for midpoints and log ranges. In this particular case, the results for midpoints tend to agree in terms of clusters with the corresponding results for log ranges. This is relatively common. It is common to have a high correlation between midpoints and log ranges that sometimes justifies that, but there are some applications where that is not the case. And there are differences between midpoints and log ranges that might illustrate some difference. It is also, in terms of the utility it is for display, it is also maybe worthwhile to note that one can display the coordinate plots into alternative ways, either putting all midpoints together and then all log ranges together, which is the default, or putting all variables together, midpoint log range, variable by variable, which was the representation that was most useful in this particular application, but for other applications, the default might be more useful, and that can be chosen as a default. One important thing to stress is that even though only the results for the best model are shown by summary print methods, the results of other methods are available and can be inspected if so desired. In this particular case, we use the common model to have a principal coordinate plot of one model that was not the best one according to BIC, but it was interesting. And the same thing can be done to show means, proportions, and so on. And that ends
And that's it for the methods. So we are now basically concluding. Along our presentation, we have at each point indicated the reference of the papers corresponding to the particular methods. At the end now, we just would like to indicate to you the main references in symbolic data analysis, that is general references. And this starts with 3 books now available, where you can find more about symbolic data analysis and in particular interval data. The first one in 2000, sometimes called within the community the Bible, Analysis of Symbolic Data, Exploratory Methods for Extracting Statistical Information from Complex Data, published with Springer, and then 2 books from Willy, Symbolic Data Analysis, Conceptual Statistics and Data Mining, or Symbolic Data Analysis and the Soda software, which was the result of one of these international European projects. The 3 papers here below are general papers that also introduce symbolic data analysis and give an overview of what was available at that time. This was already a bit dated, but I think that no other survey papers have been published since then. So we do hope that this was of interest to you all, that you are now motivated for symbolic data analysis. Today we just concentrated on the analysis of interval data, but there is a growing body of literature and also software for the analysis of histogram valid data, that is distribution, something thinner than just intervals, but still a lot is there to do, because of course when we go further, when we go out of the comfortable context of the real numbers, nothing is as we expect it to. And so everything has to be redefined, modeled, considered, and then implemented. Thank you very much for your attention. And
thank you.
Thank you. And we now stop the presentation, and we'll be happy to answer any questions that you may have.
Thank you very much. Thank you very much, Paula. Thank you very much, Pedro. It was a very nice course. I did not know much about symbolic data analysis. Now I have a general overview. Of course, I need to go and to look at the code and try it myself, but I have a general idea now. In the chat, we do not have any questions. So everyone has the links for the code,
slides,
for
and
the slides.
And please feel free to write to us should you have questions later on about the methods or the package.
Yes, exactly.
Right?
This is what I was going to suggest. You have the emails there in the slides, I think, and you can find Paul and Pedro easily online. So if you have any questions, yes, I'm sure that if you have any questions, they will be very happy to answer them. So I think we can conclude. I don't know if you want to add something else, Paul and Pedro.
No, we just want to thank you again and the whole organizing team for the opportunity to present our work and our developments to the community. And it has been a pleasure. And of course, the next step was to move to distributional data, but this would be another course.
Yeah, exactly. Okay, so Paula, Pedro, thank you very much. It was great seeing you again. Unfortunately, not in person, but I'm sure that will happen very soon.
Very soon.
And thank you again on the behalf of the local organizing committee, on the behalf of the scientific program committee. Thank you very much for accepting our invitation and for sharing your work with us. Thank you very much.
Thank you very much. Thank you.